Hello. This is the first video in which I'll be discussing some really cool things happening in Pascal's triangle. I originally set up this PowerPoint to do at a teacher workshop and at a math conference. We're going to be looking at triangular numbers, tetrahedral numbers, and many other things. You might be wondering, well, what grade level is this for? This can be for anything from grade 3 to middle school to high school to 300 level combinatorics in college. You might be wondering, isn't this just mathematical trivia? No. There are many important mathematical ideas that I consider to be deep. They're not hard to grasp, but they're deep and they can be used to solve many problems. What I'd like to do is to look at the beauty of Pascal's triangle so that we can improve our understanding and make connections between various representations. First thing I like to do is take a look at triangular numbers. Here's the first triangular number, which is 1. Here's the second triangular number, which is 3, 6, and so on. And we use the notation T sub 5 for the fifth triangular number, which is 75. And there are square numbers that look like this, pentagonal numbers, hexagonal numbers, and so on. Let's build the ninth triangular number. We're going to need a 1, 2, 3, plus 4, plus 5, all the way down to 9. The triangular numbers are very interesting. One thing about them is they are the handshake numbers. So if you have 2 people in a room, there's going to be 1 handshake. 3 people in a room, 3 handshakes. 15 people, 15 handshakes required for 6 people in a room. These numbers over here are our triangular numbers. Furthermore, the triangular numbers also tell us the number of sides and diagonals of an n-gon. So why is it that the handshake numbers are triangular? Let's say we have 5 people, A, B, C, D, and E. Here are the handshakes. And you'll notice that we get a triangle. 4 plus 3 plus 2 plus 1. Here's another picture of the triangular numbers. Is there some easy way to get these numbers? Yes. Take 2 copies of the triangular number and put them together, like with multi-link cubes. There's the first triangular number. There's another copy of it, and notice that we have a rectangle. If it's the ninth triangular number, it's 9 on that side, and 9 plus 1, which is 10 on this side, which means we have 9 times 10, which is 90, and we take half of that because we doubled it, and we get 45. And in fact, the ninth triangular number is 45. In general, if it's the nth triangular number, and we have 2 copies of it, our rectangle is going to be n times n plus 1, which means the formula for the nth triangular number is n times n plus 1 divided by 2. Now, what are some other interesting things about triangular numbers? If you take a triangular number and put it together with the next one in line, like this and this, you get a square. So the 8th triangular, for example, plus the 9th triangular is 9 squared. So the first characterization of Pascal's triangle is that to get each number in a row of Pascal's triangle, you get it by adding the 2 numbers diagonally above it. and you also begin and end each row with 1. So here's Pascal's triangle, and we have a couple of conventions. The top row is called row 0. The next row is row 1, and so on. You'll notice here, for example, row 6 has a 6 in it, which is convenient. Now, as you're going across, the first position is the 0th position, first, second, third, and so on. So, for example, to get the 5th element in row 7, this 21 right here, in order to find this, it's going to be the sum of the two numbers above it, 15 and 6. If I take a look at this number 10 right here, it was found by adding 4 and 6. Every time you have a row of Pascal's triangle, we can get the next row. So the next row would start with a 1, then we'd have 8, 7 and 21 is 28, 21 and 35 is 56, and so on. Here's a really big Pascal's triangle. It goes on to infinity. So what's the second characterization? The second definition of Pascal's triangle is that it is a table of combinations or numbers of subsets. Now, what do we mean by this? Let's take a look at what we mean by 5 choose 2. This is a notation for 5 choose 2. So we have 5 objects: a smiley face, a heart, a moon, a lightning bolt, and a star. And I want to pick 2 from here. Well, there's a pair, and so on. And the question is, how many ways can I do this? Picking 2 is also going to give you a subset of size 2. So combinations is the same as subsets. So now we have the items A, B, C, D, E in our set, and my subsets are going to be, for example, AB, AC, AD, and so on. Therefore, the number of combinations of a certain size is the number of subsets of that size. So let's take a look at a couple of examples in Pascal's triangle. If I want 5 choose 2, that's going to be in row 5, the second position. Remember, this is position 0, position 1, position 2. So there's going to be 10 subsets that have 2 elements in them. 10 choose 7 is 120. That means there's going to be 120 subsets that have 7 items if you were going to be picking from a set of 10 items. It turns out that characterization 1 and characterization 2 are equivalent. Here we are adding the 2 elements in the row above to get the element in row N, position R. This can be proved, but I'm going to say that that's beyond the scope of this video. In the next video, I'm going to be going on to characterization 3. I hope you can see my next video.